This video is intended to be an introduction to what's called compound percent change, and I'm going to use finance as an example, and the video will eventually lead you to the idea of what's called continuous growth. So I'd like to start by saying, what if you were to put your money into a bank account, let's say $100, and let's suppose that your bank increases it by 20%, and that they're going to do this one time at the end of the year. I would like to ask, how much money would you have at the end of the year? You could think of this situation as being in the form a b to the x, where your output y would be the amount of money at the end of the year. And your b value, in order to increase this by 20%, would be 1.20. And my x, my input variable, is going to be thought of as time in years. And I'm going to increase my $100 one time at the end of the year by 20% by putting time equals 1 in here. And if I did so, I'd have 100 times 1.20, which is $120. So the idea is, if you started with $100, at the end of the year you would have $120, and this would represent a 20% increase if you were to give one application of the 20%. So if you start with $100 and you get one application of the 20% interest, you would end with $120, representing a 20% increase. Now I'd like to ask a similar question. Start with $100, and I put it in the bank that is going to increase it semi-annually, meaning twice a year, at 20% interest. What the banks do is the following. They take your annual rate of 20%, convert it to a semi-annual rate of 20 divided by 2, or 10% per application, and they do this twice during the year. So what happens is, you start with $100. After 6 months, they don't increase it by 20%, they increase it by 10%, and that can be obtained by multiplying by 1.1. So at the end of 6 months, you now have $110. Now what happens is, 6 months later, when they do the second application of the 10%, they don't apply the 10% growth on the original amount, 100, they apply it to the newer amount after 6 months of $110. So that looks like this, where they took the amount after 6 months, the $110, they increase that new amount by 10%, and you end with not $120 as before, but $121. This means you get an extra dollar. To summarize the calculation, you can think of the bank taking your $100, increasing it by not 20%, but half of that, 10%, and then this would be the amount after 6 months, and then they take that new amount and they increase that new amount by 10% by multiplying it by 1.10. But this is nothing but 100 multiplied by 1.1 twice. So a simpler way to do the calculation would have been to say that we start with $100. Rather than increasing it 20% one time during the year, they increase it by 10%, and they give 2 applications of that 10%, yielding not $120 but $121, meaning that you didn't get a 20% increase this time, you got a 21% increase. So to summarize, we started with the same amount, $100, and we're getting a 20% increase, but this time they do 2 applications, or if you want, 2 compoundings of the interest, and it turned out that that gave us more than 20%. So it turns out the more applications of the interest rate, the more money you will make. I'd like to do 12 applications of the interest rate, and banks call this compounded monthly, and this is the most common compounding method. If you have a bank account, you probably get monthly statements in the mail or via email. So let's suppose we started with $100, but this time they're going to give me 12 applications of the rate of 20%, i.e. compounded monthly. What the banks do is they convert your annual rate of 20% to a monthly rate of 20 divided by 12, which is approximately 1 2/3% per month. So rather than giving me 20% at the end of the year, or 10% every 6 months, what they're going to give me is 1 2/3%, but they're going to be doing it every month. So it turns out that if you start with $100 and you increase it by only 1.6666%, remember, if you ignore the 1 and move the decimal over twice, you would notice that this increases your value by 1 2/3%, and we're going to do this every month, but we're going to do it for 12 months. So imagine raising this to the 12th power to emulate increasing my $100 by this smaller amount but doing it 12 times, you'll notice that we don't get $121 this time, we get $121.94. So notice this time we actually get a little bit more money than before. By going from 1 application to 2, I got an extra $1. By going from 2 applications to 12 applications, I got an extra 94 cents. The more compoundings, the more money you'll make. So in summary, we started with the same amount again, but this time we get 12 applications of the interest rate. This is called 12 compoundings. Think of a compounding as just an application of the interest rate. So the banks took my interest rate of 20% and divided it into 12 equal pieces, making my interest rate very small, right? 1 2/3%. And then at the end, even though they cut my interest rate down really small from 20 to 1 2/3%, because of the repeated applications, we ended with $121.94. This is because at the end of the first month, you end up with more money than what you started with. When they apply the interest rate at the end of the second month, it's of a bigger number. And in the end, we get more money. I want to exaggerate this one step further and ask, what if the bank compounded 100,000 times? This may seem crazy, but you actually can compound something 100,000 times, 1,000,000 times, 10 billion times, and the more you compound it, the closer you are to what's called continuous growth, which is considered an infinitely many compoundings. And again, a compounding is just an application of the interest. So before I lose your interest in this math problem, let me show you the formula that's oftentimes applied in this situation. It is called the compound interest formula. It's used for a finite number of compoundings. In fact, n is the number of compoundings. And you could think of using this to emulate continuous growth where n would be a really big number. So in my problem, in part 1, we did 1 application, so n would be 1. This is called annual interest. In the second phase, we moved to 2 applications, so that would be n equals 2, and this is called semi-annual. Then we moved to 12 applications, which would be n equals 12, which is thought of as monthly. Some other commonly used ones would be n equals 4, which is quarterly, n equals 365, which would be daily, and there's no end to what you could do. But here I want to show you that this formula would give you these results. So for example, since A can be thought of the future amount of money, whereas P is the initial investment called the principal. R is the nominal rate as a decimal. Sometimes banks call this the APR of a bank account. And finally we have T as time in years. So suppose I was to plug numbers into this formula and try not to think too hard about it and do my 1 application of 20%. So my P would be $100. The question was, how much money would we have in the future if we put that $100 in the bank with a 20% interest rate? That would be a nominal rate as a decimal, which would be 0.20. So in my example, P is 100, R is 0.20. That's called the APR, which is the annual percentage rate or the nominal rate. My N, occurring in 2 locations in the formula for the first case, was 1. N is the number of applications or compoundings of the interest, so N is 1. And in all these cases, we're letting T be 1 year. So we have 1 compounding times 1 year, so we have 1 application of the 20% interest. So if you simplify this out, 0.20 divided by 1 is 0.20. You'd have 1 plus 0.20. Your exponent would be 1 times 1 or 1. And 1 plus 0.20 is 1.20. You don't even want to have to think about putting the 1 in front to increase something by 20% because the formula does it for you. In fact, I've had students put 1.2 in for R because they knew that it was going to increase by 20%, and what they end up getting is 1 plus 1.20 or 2.20, which would be incorrect. At any rate, you can see that the formula gives you the $120 that we had done without using the formula in the first place. So just because you're infinitely patient, I want to redo the second part using this formula where my P was still $100 initially, and the rate is still 20%, that's 0.20 as a decimal, and we are still putting the money in for 1 year. The difference is that our N value has changed now from N equals 1 to N equals 2, and we did semi-annual compounding where we did 2 applications. So if you remember the part of the video I did this, the first thing that was done was we converted the annual rate, the annual percentage rate of 20% into a semi-annual rate of 10% by dividing by 2, and I argued that the bank was going to give you 10% interest, but you were going to get 2 applications of that. that would leave you with 1 plus 0.10, which is 1.10, and I argued that since we were squaring it, we're applying that to percent twice per year. You could see that I could do the third case by just replacing n with 12. So to summarize, you could have thought of answering all these questions by plugging in n equals 1 into the formula, and then leaving all the variables the same, except this time replace n with 2, and then leave all the variables the same except replace n with 12. Now that I want to move to 100,000 compoundings, I can argue all we have to do is replace n with 100,000. So what about 100,000 compoundings? What if we kept all the variables the same? We're going to put $100 as an initial investment, that's our principal, and we're keeping the nominal rate or the annual percentage rate 20%, that's 0.20, but this time we're going to divide that 20% into 100,000 equal pieces. Sounds like a ripoff to me. 20% divided by 100,000 is about nothing. They're going to give me almost nothing, but trade-off is they're going to give me almost nothing 100,000 times. And they're going to do this for 1 year, so t would be 1 again. If you let me go to my calculator to show you that it's going to be a little bit more than $121.94, but not too much more. You would think going from 12 applications to 100,000 would make a huge difference, but you're going to see there's a point of diminishing returns here. So on my calculator, I'm typing $100 in, parentheses, 1 plus 0.2 divided by 100,000. No worries here, is the calculator knows to divide before it adds. It knows order of operations. However, when you hit the caret key, normally you'd have to put these two numbers in parentheses, but since I'm just multiplying by 1, I won't need to in this case. So I did this, 100,000 applications of my really puny amount of interest, and I only get $122.14. So I don't know if you were impressed, but going from 12 applications to 100,000, one would think that you'd get more than an increase of $121.94 to $122.14. It turns out that the extra amount of money you get by extra compoundings gets smaller and smaller and smaller. In fact, the graph actually reaches an asymptote. Now, I'm not going to show you the calculus maneuver that converts this formula into what's called the continuous compound interest formula, but suffice it to say, if you took this formula and you let n approach infinity, what you get is a new formula. It's read a equals pe to the rt. It has all the same variables except for one. If you notice, there's no letter n in here this time, because if you're using this formula, you're assuming n is infinity. You will be told this is the formula to use if you're ever compounding continuously, meaning infinitely many times. You don't need to plug in n equals infinity. The formula assumes that n is very, very large, and this is the formula you'd get in calculus if you took this equation and let n go to infinity. And like I said, this equation, if your input was n and your output would be a, what happens is it reaches some asymptote that there's a limit to how much money. There's a limit to the amount of money that you'll get in the future, no matter how big you let n grow. So it turns out this formula for very large n values would be a good indicator of how much money you'd get if you compounded continuously. So let me back up and ask that question, where we keep the principal $100, we start with $100, we keep the rate of 20%, that's the annual percent rate, or sometimes called the nominal rate, but we change things so that it's compounded continuously. You would proceed to plug in p equals $100 for the principal, that's the initial investment. E is just that number 2.718 roughly on your calculator. R was 0.20 still. And we're going to let our money sit for 1 year again. And if I did this, I would get 100. Now I want to multiply by E. One way to do this is to hit second, ln, and you'll get E, caret, left parenthesis, and I want 0.20. This is particularly handy to have a parenthesis here if you are multiplying by something other than 1. In fact, let me just write times 1 even though it's obvious, and tell you that if it wasn't for the parentheses, it would not think of the 1 in the exponent position, so it would be incorrect if this number was anything other than 1. And notice if you did this, if you got infinitely many compoundings, not just 100,000, if you got an infinite amount of compoundings out to several decimal places, you'd see that you actually did get more money, but to the nearest cent, if you compare, you're still at $122.14, which is the amount we had at 100,000 compoundings. So because we're rounding to the second decimal place, there was no difference between our result using this formula than using this formula at n equals 100,000. Again, if you would have looked out past the second decimal place, you'd see that you actually did get a bigger number using this formula than you did by plugging in n equals 100,000 into this one. But the idea is to two decimal places, there's no difference between 100,000 compoundings and continuous compounding.